students, welcome back to our next class. Today's class will discuss regarding orthogonal vectors and based on the orthogonal vectors, some theorems also. Today I would like to explain orthogonal definition. Okay, so orthogonal is nothing but two vectors we are taking in an inner product space. Then these two vectors are said to be orthogonal if x comma inner product of x comma y is equal to 0. See, two vectors x comma y in an inner product space. This is only the theorem related to the orthogonal vectors. Space X is said to be orthogonal vectors if inner product of x comma y is equal to 0. So now with same thing we will define the definition of orthogonality in Hilbert space also. Okay, see our definition is orthogonal two vectors x comma y in, here we are taking the same definition Hilbert space. So in Hilbert space x are said to be orthogonal to each other. Orthogonal if inner product of x comma y is equal to 0, the symbolic representation is, and it is denoted by x is orthogonal to y. This is the symbolic representation. Now, based on this definition, you are having some note points. Okay, so you have to write the notes from the videos only. Okay, listen carefully and write the notes properly. Now, based on this, you are having some note points. That note points are having the proof also. Okay, see our first note point is x orthogonal to y if and only if y orthogonal to x. Right. First note point, x is orthogonal to y if and only if y is orthogonal to x. Orthogonality, now onwards we are using the symbol only x orthogonal to y if and only if y orthogonal to x. How can we say that it is? So take the LHS condition, x is orthogonal to y. Now here we have to apply the definition of orthogonality, that is inner product of x comma y is equal to 0. Okay. Now since inner product of x comma y is equal to inner product of y comma x whole bar. Okay. Now we have to apply this since part in the above line. Then it can be written as inner product of y comma x whole bar is equal to 0. Now taking the bar on both sides, then double bar becomes itself. So inner product of y comma x is equal to 0. 0 bar is nothing but 0. Then it can be written as y is orthogonal to x. Same thing we have to prove in the reverse manner. Finally the conclusion is x is orthogonal to y if and only if y is orthogonal to x. This is our note, first point with proof. Okay. Now the second point is 0 vector is orthogonal to itself. 0 vector is orthogonal to itself. See our second point now. The 0 vector is the only vector orthogonal to itself. How can we say that 0 vector is only orthogonal to itself? Having the proof also. So the next line is, suppose x is orthogonal to x. So what we have to show? This x value is 0. Then the 0 vector is only orthogonal to itself. Okay. For this, apply the orthogonality definition. Inner product of x comma x is equal to 0. So inner product of x comma x is equal to 0. Here we have to apply inner product of x comma x formula, that is norm x square is equal to 0. Then sending the square that side and eliminating the norm also. Then x is equal to 0. Then in place of x, if we are substituting the value 0 is orthogonal to itself. So this is the proof of the second node point. The 0 vector is the only vector orthogonal to itself. And third one is every vector is orthogonal to 0. Our third point is every vector is orthogonal to 0. So what is our third point? Every vector is orthogonal to 0. Very important point it is. Okay. How can we say that every vector is orthogonal to 0? For this, we are taking x be any vector. Let x be any vector. Then, so x comma 0 is equal to inner product 0. So in the inner product, second variable is 0, then automatically inner product becomes 0. Then it can be written as inner product of x comma y is equal to 0. Then the symbolic representation is x is orthogonal to 0. What is the x? X is any vector which is orthogonal to 0. This is the proof of our third node point. Okay. Now, based on these node points, I would like to explain our first theorem of today's class. See our theorem or lemma, orthogonality lemma. The statement is, let x be an inner product space and y is complete subspace of x and small x belongs to capital X is fixed. Then we have to show that z is equal to x minus y is orthogonal to y. See, in this proof, first we are writing the given conditions. Later we have to write our A. Okay? Right. See, let x be an inner product space and capital Y be a complete subspace of X and small x belongs to capital X is fixed element. Using these three conditions, we have to show that Z is orthogonal to capital Y. So what we have to show here? Orthogonality. We will say inner product of this Z comma set of Y elements is equal to 0. Now we will show this condition in the reverse. Nothing but assume that Z is not orthogonal to Y. Once Z is not orthogonality, then inner product is not equal to 0. Right. So we will do this one in the contradiction manner. For this purpose, assume that Z is not orthogonal to Y. Not orthogonality means to say inner product is not equal to 0. So that then there exists an element y1 in the Y such that inner product of x comma y1 is not orthogonal, so that not equal to 0. Also y1 non-zero. If chances is there y1 is equal to 0 in the inner product, second variable is 0, automatically total becomes 0. So that's why also y1 is non-zero element. See, here we are specifying, otherwise what will happen? See, otherwise if y1 is non-zero, 0, what will happen? Otherwise x comma y1 is equal to inner product x comma 0, then total becomes 0. Right, ma? Next line. Write beta is equal to Z inner product of here ma, we are taking Z is not orthogonal, that's why here not x Z. Not orthogonal. So that next line is write inner product of, otherwise you can take left write beta is equal to inner product of Z comma y1. This value we are taking. Then clearly which is non-zero also. Okay. Next line. Now for any scalar alpha, we have to calculate norm Z minus alpha y1 whole square value. See, once again I am telling to you, you can write the notes, you can copy the notes from the videos only. So here we are taking one scalar alpha, we have to calculate norm Z minus alpha y1 square value. Okay. Now for any scalar alpha, next line norm Z minus alpha y1 whole square. We can simplify this thing. Norm x square formula we have to write in terms of the inner product. Okay. So inner product of x comma x. So inner product of Z minus alpha y1 comma Z minus alpha y1. Now here we have to write the inner product separately. Then inner product of first comma first. Here inner product of first comma second is having the minus, so that minus Z first comma second variable. So with the first variable inner product is completed. Now with the second variable, similarly we have to write with the second variable. Second variable already having a minus, so that minus inner product of second comma first variable. Both are having the minus, so that it becomes a plus alpha y1 comma alpha y. Okay. Now norm inner product of Z comma Z formula again we have to write in terms of the inner product, so that norm this is Z square minus, here alpha is the scalar for second variable, we can write it is in front, then automatically bar exists, alpha bar inner product z comma y1 minus. Here only for first variable, so only alpha y1 comma z. Next plus. Here for first variable alpha, for second term alpha bar. Inner product of y1 is nothing but norm y1 square. You already know all these formulas. Next we have to write the values. Norm z square minus alpha bar into z comma y1 value we already took, that is equal to beta. Substitute here alpha bar into beta minus alpha into y1 comma z is there, nothing but beta bar plus here alpha into alpha bar write it as it is, alpha into alpha bar into norm y1 square. Okay. Now here we have to calculate alpha bar value. Sima, here we are taking alpha bar value. Okay. Next line, write alpha bar is equal to beta bar by norm y1 square. So here write alpha bar is equal to beta bar by norm y1 square. Using this we can simplify the above lines. So write above line LHS first. Norm z minus alpha y1 square is equal to norm z square minus alpha bar beta minus alpha beta bar plus alpha into, substitute alpha bar value, that is beta bar by norm y1 square into norm y1 square. Okay, here norm y1 square is cancelled. Now write the remaining terms. So that remaining terms are norm z square minus alpha bar beta minus alpha beta bar plus alpha beta bar. So minus and plus terms are cancelled again. Write remaining. Norm z minus alpha y1 square is equal to norm z square minus alpha bar into beta after simplification. Next line, also we have z value. Also we have z is equal to x minus y. Then calculate norm z. Next line, then norm z is equal to norm x minus y. This value is nothing but delta from the minimizing vector theorem. From that theorem you can easily get the delta formula. Delta is equal to infimum of something and norm of x minus y also there. Two formulas are there. So z is equal to clearly delta. Now therefore we have to calculate norm z minus alpha y1 square value. Okay. Using this norm z, we have to calculate z minus alpha y1 whole square value. Now if you are observing, norm z value is delta. So if you are substituting here delta square minus certain value. So delta square minus certain value means automatically this value is less than or equal to delta only. So that next line is then norm z minus alpha y1 square is less than or equal to delta square. Simply, how can we say that the value is, if you are observing norm z minus alpha y1 square is equal to norm z square minus alpha bar beta. See now, if you are taking this value is 5, then what is the chances? 6 minus 1, otherwise 7 minus 2, otherwise 8 minus 3, like this. So if you are observing this term and this term, mean to say these values and these values. Observe. Always norm z minus alpha y1 square is less than the norm z square. No chance for even equality also. Okay. Okay, now our next line is now squaring or cancel the square on both sides. Later our next line is less than delta. Let it be equation number 1. Next line again z minus alpha y1 is equal to, calculate the value. Again z minus alpha y1 is equal to, substitute z value. Z value is x minus y. Substitute that x minus y minus alpha y1. Take it minus common. Then y plus alpha y1. Now this entire thing is, take it as the y2, x minus y2, where y2 is equal to alpha plus y plus alpha y1. See now, last line is where y2 is equal to y plus alpha y1. Entire things belongs to the y only, so that y2 is also belongs to y only. Now we have to write delta formula. You already know delta is having the two formulas. One is delta is equal to norm x minus y, and the second one is delta is equal to infimum of norm x minus y bar such that y bar belongs to the y. The second formula here we are using. From this, infimum of this set of values is equal to delta. Infimum means a least value. That's why individual values are maybe greater than or equal to delta for all y bar belongs to the y. Now same thing here we have to apply for this. Norm of z minus alpha y1 is equal to norm of x minus y2. Here y2 belongs to the y. Once norm of, here we are taking norm of x minus y variables is greater than or equal to delta. So our next line becomes norm of z minus alpha y1 is equal to norm of x minus y2. X minus y2 is clearly greater than or equal to delta. So therefore norm z minus alpha y1 is greater than or equal to delta. But which is clearly contradiction to equation 1. See, equation 1 value is always less than delta, but here we got z minus alpha y1 is greater than or equal to delta, mean to say, which is clearly contradiction to equation 1. So which is contradiction to contradictions means to say our supposition is wrong. What is our supposition? Therefore, our supposition, what is our supposition? Z is not orthogonal to Y is wrong. So hence Z is orthogonal to Y. Okay, hence proved. This is our required condition. Think so, very easy theorem and important for short answer. Okay. Next, we will discuss orthogonal complements. See, the next definition is orthogonal complement. Here H is Hilbert space, Y is subspace of H. Then orthogonal complement of Y is defined by Y orthogonal complement is equal to Z belongs to the H such that Z is orthogonal to Y for all Y belongs to the H. See what is the symbolic representation of this thing? Our next definition. Orthogonal complement. So here H is the Hilbert space and Y is the subspace of H. So let H be a Hilbert space and Y is subspace of H. Then the orthogonal complement of this Y is, so then the orthogonal complement of Y is symbolic representation Y orthogonal complement and defined as Y orthogonal complement is equal to all the Hilbert space element Z belongs to the H after satisfying the condition Z is orthogonal to Y where Y belongs to capital Y element. So here Z is orthogonal to the Y elements of Y. Then this Z belongs to already in the H, same Z belongs to Y orthogonal complement. Now based on these definitions we were having some note points. These note points are very important and useful for our further theorems. Right, ma? See the note points based on this orthogonal complement. The first one is see the note points now. First one, 0 orthogonal complement is equal to H always. Second one, H orthogonal complement is 0. This one is reverse one. 0 complement is full set complement is 0. Third one is S intersection S orthogonal complements. So value goes to common element 0. We already know that thing. Intersection of set and its complement is equal to 0. Fourth one is S1 is subset of S2. When we are applying the complements, these two becomes reverse. So S2 orthogonal complement is subset of S1 orthogonal complement. The fifth one is S is subset of S double orthogonal complement. Where S double orthogonal complement can be written as S orthogonal complement whole complement. Now the sixth one is having the proof also. Okay. And that sixth point is important for short answer. See our note last point, it is having the proof. Sixth point is why orthogonal complement is closed linear subspace of H. So it is having the proof also. For this first we have to show that why orthogonal complement is non-empty, later linear, after that closed subspace. Okay? For this non-empty purpose, orthogonal complement means to say inner product of H element comma Y element is equal to 0 for all Y belongs to Y. Now this can be represented as symbolic representation. 0 is orthogonal to Y. Mean to say this 0 element belongs to Y orthogonal complement. Mean to say Y orthogonal complement is non-zero. It is having the element 0. Now for the linear purpose, we want two elements. That's why let x1 comma x2 belongs to Y orthogonal complement and alpha comma beta are two scalars. Then we have to calculate inner product of alpha x1 plus beta x2 comma y. Right? Write the inner product separated alpha x1 comma y plus inner product of beta x2 comma y. Now we can write the scalars outside. So alpha into inner product of x1 comma y plus beta into inner product of x2 comma y. If x1, x2 both are is in the Y orthogonal complement means inner product of x1 comma y variable goes to 0, x2 comma y goes to 0. See here I will write that since x1 comma x2 belongs to Y orthogonal complement means inner product of x1 comma y is equal to 0 and inner product of x2 comma y is equal to 0 for all y belongs to capital Y. This is part only for your understanding purpose, no need to write in the exams. So this value goes to 0. Again, inner product of these two variables is equal to 0 mean to say in this one h variable belongs to Y orthogonal complement. H variable mean to say this thing. So our next line is therefore inner alpha x1 plus beta x2 belongs to Y orthogonal complement. This gives Y orthogonal complement is a linear subspace of H. Next, we want to show that the closed property. For this closedness, first we are taking limit point. Let x be a limit point of Y orthogonal complement. So by applying the known theorem, then there exists a sequence in Y orthogonal complement. Sequence is converges to that limit point. Next, now for any Y belongs to Y, xn is in the Y orthogonal complement mean to say inner product of xn comma Y variable goes to 0 as xn belongs to Y orthogonal complement. Next, we have to calculate limit of inner product of xn comma Y value. It can be is equal to 0. Limit of xn comma y is equal to 0. Limit of xn is nothing but x. So x comma y is equal to 0. So x belongs to Y orthogonal complement. Hence y is closed subspace of linear. So finally, hence y is a closed subspace of Hilbert space H. Okay. Next we will discuss the direct sums in our next class.